Hi, 7th graders. This is grade 7, day 8, lesson 8-6, page 402, numbers 11 through 31, the odds. Today's lesson is about the difference between something called experimental probability, which is probability based on experience of conducting an experiment, or theoretical probability, the probability based on fact, or what should happen, but doesn't necessarily always happen. Before we get started, please read through pages 400 and 401, and then come back to this video and we will take a look at some examples. Okay, welcome back. Let's talk about what this means here first of all. I have in my hand a red die. You know that a die like this has 6 faces numbered from 1 to 6. If I were to roll this die on the table, what would you expect the probability of rolling a 1 would be? You'd expect that the probability favorable outcomes over all of the outcomes would be 1 out of 6. Likewise, the probability of rolling a 2, 1 out of 6. The probability of rolling a 3, 1 out of 6. The probability of rolling a 4, 1 out of 6, and so on. What we've been talking about so far is theoretical probability. What you expect to happen with this die is the theoretical probability. If I said to you, what's the probability of rolling a 6 on this die right now, if I throw it on the table in front of me, you'd say 1 out of 6 because there's one favorable outcome over the top of all of the outcomes, which are 6 in number. Now, what does that mean when we talk about experimental probability, the other term? The probability based on experience of conducting experiments. Before I started this video, I rolled this die 6 times on a table and kept track of what number showed up on top. And the first time I did this, I got these 6 numbers, 5, 3, 3, 5, 1, and 3. Do you notice how the experimental probability doesn't really match with what we were talking about over here? If I figure out the probability of getting a 3 in this particular circumstance, the probability of getting a 3 is 3/6 or 1/2. That's not 1/6 like we expect to happen, is it? And what if I said, what was the probability of rolling a 6 in this circumstance? Well, it was 0 out of 6 because we never saw a 6. And that's not what we expect to happen. We expect to see 1 out of 6 times a 6 appearing on the die when we toss the die 6 times. So I did it again. Here's my second set of numbers, 4, 3, 4, 6, 2, 1. Notice the number 5 doesn't even appear here at all. So if somebody said to me, in your second set of data, what is the probability of getting a 5? We'd have to say that in the experiment, it was a probability of 0 out of 6. But if somebody said, what's the probability of rolling a 4 in your second set of data, that would be 2 out of 6, which simplifies to 1/3. Notice the experimental probability doesn't match always what we think should happen, the theoretical probability. Let's take a look at this in another circumstance over here. Imagine somebody tossed 3 coins. Tossed 3 coins and kept track of what happened. And they tossed these 3 coins 80 different times and kept track every single time what happened. In this particular circumstance, they found that 6 times those 3 coins all landed heads. They found that 32 times when they tossed the 3 coins, 2 of them were heads and 1 of them was tails. They found that 30 times they had 1 head and 2 tails showing. And finally, 12 times they had 0 heads showing. In other words, all 3 coins landed with tails facing upwards. Now, notice what I did. I changed the 6 into probabilities. A probability here in fraction form, and then probability also in decimal form. In other words, 6 out of the 80 times they did the experiment, or 0.075 times, we got all heads. Or 32 out of 80 times, they got 2 heads, or 0.40. 30 out of 80 times they got 1 head, and 12 out of 80 times they got no heads. Now, let's compare that. This would be, of course, a situation where we're thinking about experimental probability. Let's look over here where I figured out the theoretical probability of doing that exact same thing. I drew a tree diagram where I talked about coin 1, coin 2, and coin 3. And then I created a sample space over here with all the different ways that those 3 coins could land. And I found out that there were 8 different ways. 1 out of the 8 ways, they landed all heads. 3 out of 8 ways, they landed 2 heads. 3 out of 8 ways, they landed 1 head. And 1 out of 8 times, they landed with 0 heads right here. That's the 1 out of 8. And then I changed them into decimal numbers as well. Do you notice how our fractions and our decimal numbers for the theoretical probabilities do not match the experimental probabilities, do they? Now, in some cases, they're rather close. And in one case, they're dead on. Look at 1 head here and 1 head here. They're dead on. 0 heads, they're pretty close. 0.125 is a very close number to 0.15. And right here, 0.375, 0.37 is pretty close to 0.40. But this one's kind of far off. 0.125, 0.12 is pretty far off when compared to 0.07. So do experimental probabilities and theoretical probabilities have to match up? No, they don't. And you know that full well if you've ever played the game of Monopoly. Do the die always land on the board in a random pattern where you see all of the numbers appearing regularly? No, sometimes people tend to see the same numbers popping up over and over again when they roll a die. Let's look at example problem 1 red. Oh, I'm sorry, let's go to the green dot problem on top of 401. Green dot problem, top of 401. It says there, what is the experimental probability that a teenager bought a candle in the last year? If you look up above, we're talking about probabilities. Candles have the number 110 attached to them on the right. 110 purchased the item. Now, how many total people were there in this circumstances? Well, if you look in example problem 4 red dot 4, it says that 200 teenagers were asked about this. So we've got a situation where the probability of picking a candle is 110, because that's the favorable outcomes, over 200, because that's all of the students that were in this situation. Can we simplify this? Yes. Divide by 10, and you get 11 over 20. So that's the answer they were seeking in that green dot problem. Now let's go back to this table over here. Remember what happened? Somebody tossed 3 coins, and when they tossed those 3 coins, they wanted to see how many times heads would appear, how many times tails would appear, and so on, and they created a table off of that. Let's talk about a few questions here. If I said to you, is a person more likely to get all heads or more likely to get no heads, what would you say is the answer to that? Is a person more likely to get all heads or no heads? Well, hopefully you would say they're more likely to get no heads, because no heads is happening twice the amount of time when compared to getting all heads. What if I said this question? How many possible outcomes are there for tossing 3 coins if order is important? If order is important. Well, I think you have to look over here at the theoretical tree diagram for tossing 3 coins. Notice how order is important over here. How many different ways were there? There were a total of 8 different ways to toss those 3 coins. Number 3, or question C, is the theoretical probability greater for tossing all heads or no heads? In theoretical probability, is the probability greater for all heads or 0 heads? The answer to that would be they are the same. Notice, 1/8, 1/8. There is no difference when it comes to theoretical probability. Okay, let's go to the top of 402, problem number 3. Problem number 3. It says, use the table at the right, which is talking about tossing a coin. Based on your results, what's the probability of getting a heads? The probability of getting a heads. Well, looking at that table at the right, we notice that heads happen 26 times. How many total tosses were there? Well, you'd have to add the 26 to the 24, and you'd get 50. Is it possible to simplify that? Yes. Divide by 2 on the top and the bottom, and here's our final answer for number 3. Let's take a look at number 4. Based on the same results, how many heads would you expect to occur if you tried this 400 times? Now, this is a new type of problem. They're asking us to predict a result based on what you found here. If this is true, how would we find this if we do it 400 times? Well, the way we do this is we create a proportion. We say, okay, 13 out of 25 times, this is coming up heads according to problem 3. Now, let's figure out how many times it comes up out of heads out of 400 times. Can anybody solve this problem? Well, it'd be 13 times 400 divided by 25. Okay. I get 208 as my answer. 208. 208 what, though? What's going to be the label for this? The label will be heads. Out of 400 times, you would expect heads to come up 208 times. Let's go to number 5. What's the theoretical probability of getting heads? Okay. Theoretical means what we would expect to happen, not what happens during an experiment. If I flip a coin, what do I expect to happen? How many times do I expect heads to happen? The theoretical probability would be 1/2, right? Number 6, based on the theoretical probability, how many heads would you expect to occur in 400 tries? So number 6 is similar to problem 4, but now we're going to use the theoretical probability and think about how that would change if we did the experiment 400 times. So instead of 13/25 equals x over 400, now it's 1/2 equals x over 400. And that's pretty easy. I think most of you can do that one in your head. X in this case would have to be 200 heads. Let's go to number 7. Compare the theoretical probability to your experimental probability. Well, when we talk about comparing, usually we have to create some sort of sentence, right? So what can I say about the theoretical compared to the experimental? Well, they're sort of close, but the experimental seems to favor heads, doesn't it? So I'm going to write that, the theoretical and experimental probabilities are close, but the experimental probability is slightly larger. That would be a good way to compare the theoretical probability to the experimental probability. Let's do number 8. What is the probability that the next car will be white? Well, they've got 4 choices of color for the white car, don't they? I'm sorry, for the cars, rather. White is 35. Red is 23. Green is 12. And other colors would be 20, right? White, red, green, and others. Let's add these numbers up first. I get 5, 10, 4, 5, 6, 7, 8, 9. I get 90. That's 90 total cars. How many of them are white? 35. So problem 8, favorable over all of the outcomes? Favorable over all the outcomes? That seems to be 35 over 90, I think. Let's double check our math here. Yep. Can I simplify this? Yeah, let's divide by 5. There's our probability of getting a white, 7 out of 18. Number 9, what if there's 180 cars? How many would you expect to be white? Oh, they're asking us to predict an outcome. We need a proportion. We're going to use this ratio and say to ourselves, okay, what if it's not out of 18 cars? What if it's out of 180 cars? How many of them would you expect to be white? Well, I'd expect, based on what I see here, 70 white cars in this particular case by solving this proportion. Okay, hope this helps you. If you have any questions, give me a call. You know my phone number. It's in your math book or it's in the emails that I send out regularly. Thank you and have a good day.